Hi, I'm Hamilton Carter from Texas A&M University. I'm going to talk today about an experimental test we're doing of the whole theory of superconductivity. First, I need to nail down a few terms. One is that a superconductor is a material that loses all resistance to electric current below a certain point, and also expels all external magnetic fields up to a certain critical field strength. Beyond that field strength, the superconducting state will collapse or quench, and the material will return to its normal state and stay there even if the temperature is still below the critical temperature. In 1957, Vardeen, Cooper, and Schrieffer authored what came to be known as the BCS theory of superconductivity, and it posits a model of superconductivity with an electron traveling through a crystal lattice, and as it does, it sets up vibrations in its wake. Now, a second electron can come along, sync up with those vibrations, I should say a second electron of opposite spin, and travel along more easily. So these two electrons are paired by an attractive potential, and as other electrons pair up, they match their phases to the phase of the original two electrons, and what we wind up with is a condensate of zero spin or boson states. It is, to break one of these states, you have to break all of the states, so it's more energetically favorable to allow this condensate to move through the material with zero resistance than it is to break any one of the pairs. Now, if the temperature gets too high, then the second electron has too difficult of a time finding the vibrations of the first, and we no longer become superconducting. BCS predicted a maximum critical temperature of 30 degrees Kelvin. So in 1986, when researchers found a superconductor at 35 degrees Kelvin, and later that year superconductors that went superconducting at 90 degrees Kelvin, it was a big surprise, and theorists set to work finding a model of how these superconductors behaved. One of the most prominent models was something called the dynamic Hubbard model, and the whole theory of superconductivity is an extension of that. Which brings us to the question of what is a hole. When we model electrons traveling through a crystalline lattice, we often model the crystalline lattice as a periodic array of delta function potential wells. If we solve Schrodinger's equation, then we find that there are bands of energies where electrons can pretty much tunnel through all the wells, and gaps where electrons get stuck in the wells. And this is what's called a band gap diagram. Now, for some materials near the tops of energy bands, we can actually solve the dispersion relation, the relation between energy and momentum, and find that we have electrons with an effective negative mass. So that means if I apply an electric field that would normally make an electron go from left to right, the electron will instead go from right to left. Rather than carry around the clunky phrase negative effective mass, most engineers and physicists just change the sign of the electron and rename it to be a hole, and then everything proceeds from there. Now, the whole theory of superconductivity, built on top of the dynamic Hubbard model, works because the dynamic Hubbard model says that holes in neighboring wells with opposite spins have what's called a hopping interaction or a hopping potential, and that they can pair up and form something that looks like a covalent bond, and when they do that, the wave functions of both of the holes spreads out. Now, as their wave functions spread out, they go down in kinetic energy. As they drop in kinetic energy, they fall down through the energy band, and as they reach the bottom, they behave like undressed electrons. So once again, we have a pair of electrons with opposite spins, just like in BCS. The difference here is that what the whole theory of superconductivity hypothesizes or says is that as the wave functions spread out, these opposite spin particles are moving out through an electric field, and they develop a counter-rotating azimuthal velocities or opposite azimuthal velocities. And so now, at the end of the day, we have two opposite spin particles rotating around the center in opposite directions. So we have a net zero current charge, but a net positive, or a charge current, and a net positive spin current. Within the material, these spin currents cancel, but what that leaves is a net spin current along the surface of the material. It's that net spin current that we're going to talk about. potential energy is in the hundreds of keV. What the full theory of superconductivity predicts is that if you quench this superconducting state, these electrons will fall back into the material, releasing that potential energy as Bremsstrahlung or X-ray radiation. And we intend to look for that X-ray radiation. We're going to take a lead sample, bring it into a superconducting state by cooling it with liquid helium, quench it by pulsing it with a 2 kilogauss magnetic field over the space of about 100 microseconds, and watch for the X-rays to come out using the sodium iodide scintillator and photomultiplier tube. So far we have gathered and characterized all the equipment we need for the experiment. We started out looking at a glass Dewar. It offers little attenuation to X-rays, but its sample space is very small, and energy of the X-rays goes with radius of the sample. So we looked at some other candidate Dewars. The two on the left have very large sample spaces, but they're aluminum, so they offer a lot of attenuation to X-rays. And the one on the right that we finally arrived at is a biomedical Dewar. It's going to allow us to get the sample down in this nice little pink mill. It's going to have fiberglass, so we can attenuate X-rays much. And we can get the simulator right up against the sample and get a nice big solid X-ray field just to the simulator. It's a 3-inch base sodium iodide crystal, magnetically sealed with a photomultiplier tube. We fielded it with lead bricks, and we tested it with the sources in the Dewar. And it is linear between 22 keV and about 500 keV of X-ray energy, so it fits the bill for what we need. We have also tested it near the pulsed magnetic field that we're going to use, and found that the background was caused by the pulsed magnetic field was negligible. We have also, that brings us to the pulsed magnetic field, and for the pulsed magnetic field we're using a can crusher demo. We found an article about this in American Journal of Physics. Dr. Silva was kind enough to forward us the simulator that he had written for his can crusher, and we have been using that simulator to calculate what kind of magnetic fields and currents we can expect out of the can crusher supply, and they fit the bill for what we want to do with our experiments. You can see here we looked at a large radius sample and a small radius sample. With the small radius sample we can drive quite a bit more current through the coils, the magnetic coils, than we can with the large radius sample. We can take that current and calculate our maximum magnetic field. So you see a smaller sample of 2 centimeter radius, the magnetic field is well above the quenching field for lead out to the maximum radius of the sample, and with a larger sample our magnetic field falls quickly below the critical radius. So, we intend to complete the experiment this semester, publish our results, and report them at the March meeting, as well as at the March Texas Academy of Sciences meeting. They are actually funding our liquid helium. Other research we can do is to look at the triboelectric effects that this theory predicts. As that cloud of circulating spin current comes out of the sample, is predicted that there may be some excess charge at the surface. And also, as those electrons spread their wave functions, it is predicted that the potential of the atoms near the surface will actually change, and this should be visible using electron diffraction. Thanks for your time.